For each positive integer n, let f1 of n be twice the number of positive integers of f, divisors of n, and for j is greater than or equal to 2, let fj of n equal f1 of fjn minus 1, and for how many values n less than or equal to 50 is f50 of n equal to 12. Okay, the first thing you can realize is, hey, at 50 of n, we're just applying f1 to n 50 times. That's what that's the definition of f50. So like, for example, if I had like, I don't know, 32, I apply f1 of n to this, I get, well, 32 is equal to 2 to the 5. So it has 6 factors. So f1 of n is 12. 2 times the number of factors. Now let's try something else. Let's try to do it again, because there's no guarantee, even though f1 of 32 is already 12, there's no guarantee that f50 would also be 12. So let's try f2 of 32, which is f1 of the previous term, f1 of 12. Hey, 12 is equal to 2 squared times 3. How many factors is this? Well, the formula for the number of factors is each of the powers of the primes plus 1, all of them multiplied together. This is 3 times 2, which is 6. So f1 of 12 is equal to 2 times the number of factors of 12, which is 12. Oh, that's really, really nice. We've already found something. We found that if f anything of n is equal to 12, if you keep applying f, you'll still end up with 12 no matter what. So even if f3 of n was 12, f50 of n would be 12, because if you apply f47 more times to f3 of n, you're still going to get 12, because f1 of 12 is 12, 47 times. Okay, so this problem becomes a lot nicer, which is that, hey, we just need to get to 12 at some point after applying f. And the trick is 12 is one of the few numbers, very few numbers below 50 that actually has f1 of 12 equals to 12, f1 of itself equals to itself. Turns out after some experimentation, the only other number that does that is 8, and you can check that on your own, but we're not even going to need that in our solution, because for f anything of n is equal to 12, let's work backwards. f50 of n is equal to 12. So f49 of n, f1 of f49 of n is equal to 12. What does this mean? It means f49 of n has 6 factors, because f1 of anything is the number of factors it has plus 2, and these factors are positive integers. Okay, what does that mean for it to have 6 factors? Well, we know that for any number, let's just take a look at any number x. We're going to call this p1 to the e1 times p2 to the e2, etc. And let's say it has k prime factors, pk to the ek. What's this representation? Is just, hey, x is equal to first prime to the first exponent times the second prime to the second exponent, etc., times the kth prime to the kth exponent. That's all there really is to it. The number of factors of x is actually going to be equal to e1 plus 1 times e2 plus 1 times, etc., times ek plus 1. So you see, hey, if f49 of n has 6 factors, then we must have 6 is equal to this stuff, right? And since each of these exponents is a positive integer, we must have each of these things is going to be at least 2, because each of the exponents is at least 1. Otherwise, it wouldn't be in the prime factors. So you can quickly realize that the only possible way for this to happen is for 6 to equal 2 times 3, or 6 to equal 6. In which case, e1 is 1, e2 is 2 for the 2, 3 case, or e1 is 5 and there aren't any other exponents. So you see that f49 of n is equal to p1 times p2 to the power of 2, where p1 and p2 are positive primes. Or f49 of n is equal to p1 to the power of 5 for some prime. And all of these numbers, they really have to be less than, what is it? has to be less than 50, less than or equal to 50, right? So we can list all of the numbers less than or equal to 50 that satisfy this. For fifth powers of primes, the only real one is 32. That's the one we started out with. 32 is 2 to the power of 5. It's the only power of 5 that's less than 50, besides 1, which isn't a true power of 5 because 1 is not a prime. Okay, then for P1 times P2 squared, let's do some casework based on what P2 is. So if P2 is equal to 2, then F49 of n becomes 4P1, right? And therefore P1 can equal 3, it can equal 5, it can equal 7, and it can equal 11. And it can't equal anything higher because think about it. For numbers less than or equal to 50, no matter how many times you apply f, there will never be a number where f of something is greater than 50. And that's just a pure fact, right? If you were to have like 48, f of 48 is clearly not greater than 50 because no number can have more divisors than the number. The maximum number of divisors 48 can have was 1, 2, all the way up to 48. So obviously, no matter, even if we count the illegal factors that are below 48, you can never get anything greater than 50, which means we only have to test up to 50. So possible values of F49 of n could be 4 times 3, 4 times 5, 4 times 7, and 4 times 11. Now let's say that P2 is equal to 3. So F49 of n becomes 9P1. Now we could have P1 has to be different from P2. Otherwise, you're not really getting anything. If they're the same, you're just going to have P1 to the power of 3, which does not have 6 factors. So P1 can be 2, P1 can be 5, and that's it. So 18 and 45 are also possible values of F49 of n. Now, what if P2 is equal to 5? So P1 times P2 squared is 25P1. And the only possible value of P1 is 2. 25 times 2 is 50. And obviously, you cannot have anything higher than P2 equals to 5. Otherwise, F49 of n will become greater than 50, which we've already stated was impossible. So these are the possible values of F49 of n. Now we could go ahead and say, well, hey, if F49 of n is 12, then these values could be for F48 of n or F47 of n. And actually, since each of these numbers has F1 of itself equal to 12, F50 of itself is also equal to 12. So these are actually all solutions. However, we're not done because F48 of n could be equal to one of these, right? F48 of n could be equal to 32, 12, 20, etc., etc. Any of those solutions. However, you can realize that, hey, the numbers below less than or equal to 50, there honestly can't be that many factors, right? And it really turns out the most factors a number below less than or equal to 50 can have is 10 factors, which means the maximum number of f of n for n less than or equal to 50 is 20, 2 times 10, which means F48 of n is equal to 12, 18, or 20. The solutions to F48 of n equals to 12 are F47 of n equal to all of these. Now, if F47 of n has 9 factors, and therefore 2 times 9 is 18. 9-factor number must either, because remember, take a look at this formula, either be an 8th power of a prime or P1 squared times P2 squared. For 2 distinct primes, P1 and P2. Those are the possible values that satisfy 9 factors. And you see that the only number less than or equal to 50 that satisfies any one of these forms is 36, which is 2 squared times 3 squared. What else? If a number has 10 factors, take a look at the number of factors formula. You're either going to have a prime to the power of 9 or a prime times another prime to the power of 4. And the only number that satisfies that requirement is 48. So F47 of n can be equal to any of these. And guess what? F46 of n, it turns out, has these exact same solutions because really only 12, 18, and 20 are actually possible for F46. And so on and so forth. So we can conclude that n itself has to be one of these numbers. And there are 10 solutions, and therefore we are done. You can count them up, 10 solutions, and we're done. Thanks for watching, and I'll see you next time.